Hi, class. So this is our last lecture in chapter 17, and this will be on 17.4. And we're going to work two worksheets, worksheet 30 and 31. And so you might want to have those handy. So I'm going to start the PowerPoint. And hopefully you can see the PowerPoint. So chapter 17.4 on potential, free energy, and equilibrium and how they are connected. So that's the purpose, is to show the relations, and these are equations between the potential, cell potential that we already discussed in the last section, free energy change, which we discussed in chapter 16, and equilibrium constants, which we discussed in chapters 13, 14, and 15. So this is almost a culmination of what we've learned in chapters 13, 14, 15, 16, and 17. We're going to use information from all of those chapters in this unit. So we'll be involving calculations involving the relations between cell energy and cell potential, free energy, and equilibrium constant. Lastly, we'll use a Nernst equation. It's a so-called Nernst equation, which relates cell potential under non-standard conditions. So we'll see what that is. And as I already said, we'll be doing worksheets 30 and 31. So potential, cell potential, free energy, and equilibrium. Previously, we talked about, in the last section, we said that galvanic cells with a positive cell potential lead to spontaneous reactions. And in fact, if you set up a galvanic cell with a negative cell potential, it wouldn't operate the way you've set it up. It would go backwards. Okay, so cells always operate in the direction that where they have a positive cell potential. And that happens until the reaction runs down when you run out of reactants. And as the cell reaches equilibrium, then it stops. So when you run out of reactants producing products, at some point you're going to reach an equilibrium state, and the cell potential is 0. So you have to keep in mind that the cell potential and the standard cell potential are different. The standard cell potential is a cell potential under very specific conditions, but the condition that you set up the cell might not be at those standard conditions. And so we're going to learn how to calculate the cell potential at non-standard conditions. That's at the end of this lecture. Similarly, we discussed that if the cell potential is negative, then the redox reaction is not spontaneous, and the reverse reaction is. Okay, that's a summary of what we've covered previously. Now let's go back. Let's look at the relationship between cell potential, free energy, and equilibrium constants. They all provide measures of spontaneity. So in this chapter, we talked about cell potential. Positive cell potential indicates that a reaction will be spontaneous. In the last chapter, chapter 16, we talked about free energy. If free energy is negative, that also indicates the reaction is going to be spontaneous. And previous to that, we said if we know what the equilibrium constant is, if it's greater than 1, that means the reaction is going to shift towards product. So that means it's going to be spontaneous. And the converse is true. If the cell potential is negative, the reaction is not spontaneous. If the free energy is positive, the reaction is not spontaneous. And if the equilibrium constant is less than 1, the reaction is not spontaneous. So that's summarized here. So So let's look at the free energy. Chapter 16, what we if you read the chapter, I don't think I said this in my lecture, but if you read the chapter, that free energy is an indication of the maximum work that a system can do. And the maximum work the system can do, if they talk about reversible reaction, it occurs in a reversible reaction. But, and they said, you know, if the reaction is pretty close to equilibrium, it's reversible. But anyway, this was a statement that the maximum work that a system can do is equal to the free energy of that system, the standard free energy. The remember, we go way back, the definition of energy is something that can do work. So in terms of a galvanic cell, the work that a galvanic cell can do is electrical work. And that electrical work comes from the flow of the electrons. And some of the diagrams of galvanic cells showed a light bulb attached to the wire between the cathode and the anode. And when the current flows, you can light up that light bulb. That produces heat, produces light. If you had an electric motor attached to it, you could spin that motor. So that's where the work comes from. So the work comes from the flow of electrons. And so that's shown in these next two equations, that electrical energy is equal to minus n, where n, I'm going to talk more about this equation in the next slide, but n is the number of electrons. F is a constant called the Faraday constant, and E cell, that's the standard cell potential. That's in volts. And so we can summarize that the free energy of the cell, the free energy change of a galvanic cell, is equal to minus n F E naught cell. Now, electrical energy is commonly measured in watts. So when we've measured the free energy of the cell, that's going to come out in joules. So that's joules, you know, there's all kinds of units of energy. So joules is one of those. But electrical energy is commonly measured in watts. But if you look at this equation, if we substitute watts for the free energy, if we just put in some units, watts equals amps, that's current, that's the flow of electrons, that's the NF part of this equation, and the volts are the cell potential. So you might be familiar with this equation. This is what electricians use, and if you take physics and study electricity, you probably use this. Watts equals amps times volts. We're not going to use this in this class. All of our energy calculations will be in joules. And we're not going to talk about amps, but amps is the number of electrons times the current. In lab, if we did a lab, I don't know if you can do this in lab, but if you were able to measure the current, you could calculate, you can measure the current in amps, and from that you can calculate the number of, you know, the moles of electron that are being produced or something. Because we can measure amps, we can measure volts. We have instruments to do that. So the relationship, so the the equation for free energy in terms of cell potential is shown here. Delta G naught is equal to minus NFE. And the naught indicates standard conditions. And just as a review, we know the standard conditions is 1 atmosphere if we're dealing with gases, or 1 molar if we're dealing with solutions. And the temperature would be 25 C, which is equal to 298 K. So those are the standard conditions that we're familiar with. Delta G naught's the standard free energy. E naught cell is the standard cell potential, which we learned about in the last section, 17.3. And you can calculate that if you know the redox equation. The chemical equation for the redox reaction, you can calculate the standard cell potentials from the standard half cell reduction tables that we have already used. N is the number of moles of electron transferred in the balanced redox reaction. And balanced reaction is really important. So when we get to the problem solving part, the first thing we're going to do is balance the equation. And you can write an equation from the cell notation. Remember, we learned how to write cell notation in section 17.2. Well, from that, you can write a balanced equation and determine how many electrons, the number of moles of electrons that are being transferred from the anode to the cathode. F is a Faraday constant, and that's a constant that's used to convert from coulombs of charge. We use that to when you multiply that, that's coulombs of charge per mole. And when you multiply it, coulombs is current. And when you multiply it times the number of electrons, the moles of electrons, you get coulombs of current. The unit that we're going to use is joules per mole volt and in our equations. But joules per mole volt is the same as coulombs per mole. And that comes from the relationship between volts and joules and coulombs. 1 volt, if you remember, 1 volt was 1 joule per 1 coulomb. And this is, if you remember in the previous section when we talked about volts, I think I had one slide that showed how many coulombs of charge there are in 1 electron. Wasn't very much. It was something times 10 to the minus 19. Well, if you multiply that times Avogadro's number, you get Faraday. So this is the number of coulombs per mole of electrons. It's called the Faraday constant. So lastly, notice that delta G and the standard free energy and the standard cell potential have opposite signs. So, and that has to do with the fact that the minus NFE is electrical work. That's the work that the system puts out. That's the work that the system does on the surroundings. So you'd give that a negative sign. And that matches the delta G, that if delta G is negative, the reaction is spontaneous. So now we're going to go on. Let's see how we get the relationship between delta. We already know the relationship between delta G and equilibrium constant. We learned that in chapter 16. Now we can relate equilibrium constant to cell potential, to standard cell potential. So we learned previously that the free energy change, the standard free energy change, is equal to minus RT log K. And we just learned in the previous slide that delta G is also equal to electrical energy, free energy in terms of cell potentials minus NFE. So we can relate the equilibrium constant to the cell potential, and we get the standard cell potential is equal to RT over NF times the log of K. That derives directly from the equation, the equation up here that I'm scanning my cursor on. So these experiments, so we talk about standard cell potentials and the equilibrium constant under standard conditions, we know the temperature is 298. So if we put 298 in here, and R is 2.31 joules per mole K, we can calculate this constant. This is a constant value. This would never change at 298 K. So that turns out to be 0.257. So we can simplify this equation for standard cell potential by doing this calculation ahead of time. And this is a pretty convenient equation to use. So the standard cell potential is equal to 0.0257 volts over N, which is the number of electrons in the balanced equation that go from the anode to the cathode, times the log of K. So we can calculate K from this, knowing the cell potential. And we have one of the worksheets, I think the very first worksheet, will be doing this calculation. Now this 0.0257, you have to remember, only applies at 298K. If you're going to measure the cell potential at different temperature, then you'd have to use RT over NF. Note that if the standard, or if the cell potential is positive, look at this, if the cell potential is positive, then K is going to be greater than 1, which you know, those go together. Those both are required for a spontaneous reaction. So K greater than 1 represents a spontaneous reaction, and an E naught cell greater than 1 is also representative, or also occurs with a spontaneous reaction. On the other hand, if the cell potential is negative, then the reaction is not spontaneous as written, but the reverse reaction is. Remember that, you can always write it the other way and it would be spontaneous. And the correspondingly, for a non-spontaneous reaction, the equilibrium constant is less than 1. That means the reactants, the equilibrium constant favors reactants, right? It's going to just stay on the reactant side. It's not going to produce any product. So here's a triangle that relates these three properties of the energy properties that are, or I should say, properties that describe spontaneity of a chemical reaction: the equilibrium constant, the cell potential in a redox reaction, and the free energy change for any system undergoing change. And this came right out of your book, so you can find it when you do your reading. And this is a summary of what we already talked about, where if these all go together, if the equilibrium constant is greater than 1, so for a spontaneous reaction under standard conditions, if the equilibrium constant is going to be greater than 1, the free energy change would be less than 0, and the cell potential would be greater than 0. I think previously I said the cell potential has to be greater than 1. I was wrong. The cell potential has to be greater than 0, positive. There are lots of cell potentials that aren't greater than 1, but still represent spontaneous reactions. So the cell potential has to be greater than 0. The free energy has to be less than 0. And the equilibrium constant has to be greater than 1. If the equilibrium constant is less than 1 and the free energy is greater than 0 and the cell potential is less than 0, the reaction is not spontaneous. The third condition is if the free energy is 0 and the cell potential is 0 and the equilibrium constant is 1, the reaction is at equilibrium. So in a galvanic cell, that's what happens when the electricity stops. And in the case of a battery, in the case of a battery, we would say the battery's dead. Okay, the chemicals are still there, but they're at equilibrium, and so there's no more electron flow from the anode to the cathode. So when the cell reaches equilibrium, electron flow stops, the chemicals are still there, but they're in equilibrium, K is equal to 1, and the free energy change is 0, and the cell potential is 0. All right, so let's continue. So let's look at the concentration. So we said previously, we've been talking about cell potentials at under standard conditions, which are 1 atmosphere and 1 molar concentrations. But oftentimes we want to know what the cell potential or the free energy is at non-standard conditions. And when we study free energy, we did see an equation for that. Before we get to that, let's talk about qualitatively what happens to a cell if we change so in terms of the K, remember K, the equilibrium constant, is the concentration of products over reactants. So if we increase, and remember K greater than 1 is going to favor products. And so If you increase the concentration of, think of Le Chatelier's principle, if you increase the concentration of reactants or decrease the concentration of products, the reaction is going to go forward, so the voltage will increase. So think about that. K is products over reactants. If we increase the, or just think of the equation, the chemical equation, if you increase the reactant side, you're going to force the equilibrium to go, or you force the reaction to shift to product. And that means that in a redox reaction, where to shift reactant to product, electrons have to flow. And so that means voltage will increase. On the other hand, if you decrease product, you can also force electrons to move towards the cathode, and the voltage will also increase. On the other hand, if you increase product, you're going to decrease voltage. Or if you decrease reactant, because you're going to force the reaction to shift back towards reactant, which means it's going to stop it. It's going to slow it down. So this is some qualitative aspects of what you can do with concentration. In the next slide, we're actually going to look at cell potentials that are not at standard conditions and how the ratio of reactant to product or product to reactant will affect the cell potential. So remember in chapter 16, we had the equation delta G equals delta G standard under standard conditions plus RT log Q, where Q was the reaction quotient, which is the ratio of products over reactants. So Q is not at, remember it's like the equilibrium. If Q equals to K, the reaction is in equilibrium. But we're going to do these calculations with Q at a different concentration other than equilibrium, okay? And in this case, we're not really comparing Q to equilibrium. We're just plugging our values, our concentration values, and to determine the free energy, or in this case, we're talking about galvanic cells. We want to calculate the cell potential. And so this slide here just shows a derivation of how we can change from free energy to cell potential. So in this case, we have what we end up with is the cell potential is equal to the standard cell potential minus RT over NF times log Q. And if we do this at 298 degrees, we can, this is the equation becomes E cell equals E standard cell potential minus 0.0257 over N times log Q. Now, the temperature at 298 degrees, this is just room temperature. That's all this is. Remember, standard conditions, the E naught cell occurs when the solution concentrations are both 1 molar. But that's not what we're doing here, okay? They're not, if they were 1 molar, then it would be E cell. If they're both 1 molar, log Q becomes 0, and E cell becomes E naught cell. So the cell potential would be equal to the standard cell potential. But we're talking in conditions other than 1 molar. And in our example problems, you'll see that. So this is called the Nernst equation. So the Nernst equation has both these forms that my cursor is scrolling around, okay? So the general form of the Nernst equation is up here in the middle of the screen, and the specialized form at 298 degrees is down at the bottom of the screen. In your book, they have an equation where they have a base 10 log, and it's 0.057 something, but they have a mistake in the equation. They have E cell equal minus E standard cell, and that's wrong. There's no negative sign in front of that. So the equation in the book is not correct. Okay, so this is the correct equation. And because our free energy, I mean, our other equations are in natural log EQ. I didn't see any reason why to change it to base 10 log EQ. So this equation is natural log. So a summary of the equations that we've learned in this chapter for galvanic cells. So back in chapter 17.3, we learned how to calculate the standard cell potential from the half cell potentials at the cathode and at the anode. And remember, the cathode reaction is reduction and the anode reaction is oxidation. We did minus E anode because it was the opposite, because the tables are for reduction reactions, but the reaction at the anode is oxidation, so we had to change the sign if we're going to use the value off the table for that reaction. We just learned that the free energy for a cell is minus NFE standard cell. The standard free energy is equal to minus N, where N is the number of electrons in the balanced equation moving from the anode to the cathode, times Faraday constant times the standard cell potential. And then we also learned that we can calculate the equilibrium constant from the cell potential. And at 298, that becomes 0.0257 volts over N times log K. And then we also just learned about the Nernst equation, where the cell potential is equal to standard cell potential minus RT over NF log Q, where Q are the concentrations of the species in solution. Now remember, many of our reactions include solid electrodes. Well, the solid electrode, remember, solids don't appear. Solids or liquids don't appear in the reaction quotient. Only gases and aqueous species. So that's it for now. So I'm going to stop the share and do a couple of problems on these worksheets. And I think, I don't remember exactly which one. It might be worksheet 30, I think, is the one I wanted to have you turn in. There's only one problem on worksheet 30, and I'm going to go through the whole thing. So it should be pretty easy for you to follow this and turn it in. And then I'll do worksheet 31. So I've already solved these problems. I'm just going to walk you through the solutions. So I'll stop my share here. And by stopping the share, you should see the worksheet now on your screen. And this is worksheet 30. So the problem says, for the following voltaic cell at standard conditions, calculate the standard cell potential, the standard free energy, and the equilibrium constant at 25C. Well, that 25C makes it pretty convenient because I gave you a simplified equation. Right here, this is 298K. I gave you a simplified equation for some of these values at 298K. So let's see what we have. So anyway, if you want to use the full equation, here's the Faraday constant. Here's the R value that we would use in these equations, 8.314 joules per mole K. And then the value for volts. Our reaction that we're going to be doing, here's the half cell. So it's a reaction between calcium and aluminum, and the standard reduction potential for the calcium reaction shown here, minus 2.87. And the standard reduction potential for aluminum is minus 1.66. Notice they're both negative. Right here, from looking at these, remember the half cell reaction, the half cell reduction potential that is the highest, or the half reaction that has the highest reduction potential is going to occur at the cathode. So right now, which one's highest? They're both negative, but the aluminum is higher, is a larger, I'd say, closer to the positive than the calcium. So the aluminum reaction is going to occur at the cathode. So you can just look at these and you know that this is going to occur at the cathode. Reduction occurs at the cathode. And this is the anode reaction. So whenever you look at cell potential, half cell potentials, you should reduction potentials. Keep that in mind. You know, think about which reaction is going to occur at the cathode and which one occurs at the anode. So here's our cell notation, the galvanic cell notation for this reaction. And notice the concentrations of the ions are 1 molar. That means it's under standard conditions. So in this one, we have a calcium electrode immersed in a calcium 2+ solution. And then there's a salt bridge. And in the other cell, and this is the anode side. And then on the cathode side, we have an aluminum ion solution, an aluminum 3+ solution at 1 molar, and an aluminum electrode. And then these electrodes are connected by a wire. So what we did last time was sketch a cell. You could sketch a cell from this description of this notation for this galvanic cell. So step 1 in solving these problems is to write the reaction. You have to, the reason why you want to start with the reaction, we can just write the reaction. We have the half reaction, we don't have the whole reaction. This is the reaction that's going on, because what we know is that calcium is on the anode side, so it's being oxidized. So that means it's a reactant. So the calcium, we put the calcium here, it's going to be oxidized to calcium 2+. So since it's being oxidized, the oxidation product is on the product side of your reaction, correct? So calcium goes to calcium 2+. The calcium is on the reactant side. The calcium 2+ is on the product side. So when you see your half reactions, that's the half reaction for this has to be flipped for calcium to be oxidized. So this is at the anode, but the reverse reaction is what's going to happen at the anode. This reaction isn't happening at the anode. So the reverse reaction is calcium going to calcium 2+. The reduction occurs at the anode. That's aluminum 3+ going to aluminum. So your whole reaction, when you combine those two half reactions, looks like this. The thing is, though, it's not balanced. So we have to balance it, and we have to figure out how many electrons are being transferred. So that's what's important. So if you figure out how many electrons are being transferred without balancing it, then that's what you need to know. You don't necessarily have to balance it if you can figure out how many electrons are moving between the cathode and the anode. But remember, that's on the way to balancing a redox reaction. That's what we determine. So I'm just going to do the whole thing. I'm going to balance it. So we have to split it back into half reactions that are occurring. So the half reaction at the anode, this is the anode, oxidation at the anode, is calcium going to calcium ion plus 2 electrons. So right away, we know that to form a calcium 2+, we've had to lose 2 electrons. So these electrons leave the anode and they arrive at the cathode. So they leave the anode, go through the wire, they arrive at the cathode. When they get to the cathode, they combine with the aluminum 3+ to make aluminum. But we're losing 2 electrons. Aluminum needs 3. So that's right away, it's not balanced. We'll get to balancing it. The half reduction reaction is aluminum has to pick up 3 electrons. So aluminum needs 3 electrons coming through that wire, each aluminum 3+ ion, to produce aluminum solid. That's the reduction. So what do we do? How do we fix this? So we learned when we balanced equations way back in 17.1 is that we have to find a common denominator or a common value that we can multiply or divide the 3 and the 2 in. And in this case, the easiest way is to multiply 3 times 2, we get 6. And so if we make 6 electrons, then moving from the anode to the cathode, well, we can figure out how we can get 6 electrons from the calcium half reaction and how we can receive 6 electrons from on the aluminum side at the cathode. If we multiply the calcium half reaction by 3, we get 6 electrons. And if we multiply the aluminum half reaction by 2, we get 6 electrons. So that's what I did in the next 2 lines. Oop, you can't see it. There we go. There's the next 2 lines. That's what I did in the next 2 lines. And we can see right here, this is what we're after. We have 6 electrons being produced by the calcium and 6 electrons being picked up by the aluminum. So now we can combine these half reactions into a full reaction. And what we end up with 3 calciums plus 2 aluminums go to 3 calciums plus 2 aluminums. Now we don't really need this reaction. We don't do any stoichiometry in these problems. But what we do need to know is how many electrons are being transferred. And we learned that right here, up there. And I circled it here. N is equal to 6. So in all of those equations that we looked at, several of them contained the number of electrons that were being transferred. And in this particular problem, it is 6 electrons. So the next step is to, now we're ready. We haven't even gotten to solving this problem. It said to calculate the standard cell potential. Now we can calculate the standard cell potential. We didn't really need to know the number of electrons to calculate the standard cell potential. We just used the half cell potentials, the reduction potentials that were given right at the beginning. And the formula for that is the cathode cell potential minus the anode. The cathode, if you look up above, is minus 1.66. We're going to subtract the anode cell potential, which is minus 2.87. That's going to give us a 1.21 volt cell potential for this reaction. So that's positive. That means, okay, we set it up right. It's going to produce some electrical energy. It's 1.21 volts. You know, a common alkaline battery that you can buy at the grocery store, you put in your flashlight, is 1.5 volts. Just an aside. So anyway, this battery, if we made a battery out of calcium and aluminum, it would be 1.21 volts. So the next step is to calculate the free energy that this cell is producing. And our equation is minus NF standard cell potential. So our N is 6, our Faraday constant is 9.6485 times 10 to the 4th joules per mole volt. And our cell potential right up above is 1.21 volts. We multiply those together and we get minus 7 times 10 to the 5th joules per mole. So usually free energies are large numbers. So we usually report those in kilojoules per mole. So I did that here. So this turns out to be 700 kilojoules per mole. And it's a negative. Negative 700 kilojoules per mole is our free energy change for this reaction. That's pretty big. And it's negative, which indicates it's consistent with a spontaneous reaction. So the last thing we want to do then is to calculate the equilibrium constant. And our equation for calculating the equilibrium constant is RT over NF log K. We need to rearrange that. Well, let's see. Let me back up a little bit. At 298 and 1 molar, the standard cell potential is equal to 0.0257 volts divided by N times log K. Remember, this is our shortcut. We already calculated that previously. We took the RT over F and we got 0.0257 volts. That's over N. times log K. Well, we need to rearrange this to get log K. So log K is going to equal, multiply both sides by N. We get N standard cell potential divided by 0.0257. That'll give us our log K. So when I do that, I'll plug in the values. Log K is 6 times 1.21 volts divided by 0.0257 volts. That equals 282. So that's the log K is 282. To find K, we're going to take it e to the power of 282. And when I did this in my calculator, I got an error message. So my calculator wouldn't do this. This is too big of a number. So I had to do it on my my phone. My scientific calculator on my phone was better than that. And so when I did it on that, I got a value. It's 2.95 times 10 to the 122 is equal to equilibrium constant. Whoa, that is huge. I don't know if I've ever seen such a big equilibrium constant before, but that's typical of galvanic cells. They have huge equilibrium constants, which means that this cell is going to run until there's no reactant left, virtually, right? Maybe it's a few molecules. So it's going to keep producing electricity until there's nothing left on the reactant side. There won't be any more calcium, and there won't be any more aluminum ion. They'll be totally depleted. All right, so that's the end of that problem. It's kind of a lengthy problem, but you know, if you do a couple of them, it doesn't take too long to do them. You have to take care of the signs, be careful of the signs. It's really important to calculate, you start with a balanced equation to know how many electrons are being transferred. Okay, so quickly I'll go to the second worksheet. This is using the Nernst equation. Remember, the Nernst equation is used to calculate the cell potential at non-standard conditions. And so in this case, we're still going to calculate it, the cell potential at 25 degrees C, but the concentrations are going to be different. So here's our cell notation here, and it's chromium going to chromium 3+ at the anode. And the concentration of the chromium ion is 1 times 10 to the minus 3. And then on the cathode side, we have nickel being reduced, and this concentration is 1.5 molar, clearly not 1 molar. And the nickel 3+ or 2+ is going to nickel. I'll enlarge this a little bit. There we go. So the reaction is shown here on the right side. So you always want to write down the reaction so you know what's going on. So the chromium, especially in this problem with the Nernst equation, because we have to write the Q. And remember, the Q is the concentration of the aqueous or gaseous species on the product side divided by the aqueous or gaseous species on the reactant side. So you have to have a balanced equation to be able to do that. And the coefficients are important in the Q. So you have to make sure you include all those. And you know what? I think I messed up when I did this, because I didn't use the coefficient. So nickel, the nickel has to be cubed. I'm going to have to redo this then. And the chromium, which is the product, is going to have to be squared. Okay, so my answer is going to be a little bit different. Just realized I made a mistake. Okay, so first step one, balance the equation. So we have our oxidation and reduction half reactions, and we need to plug in, we have our half reaction to plug in the electrons, on the product side for oxidation, and we plug in the electrons on the reactant side to balance the oxidation and the reduction that's going on. Okay, next we want to balance the electrons. So these equations are pretty easy to balance. So we'll multiply the chromium oxidation by 2. We get 2 chromium going to 2 chromium 3 plus 6 electrons. And we multiply the nickel 2 plus half reaction by 3. So we get 6 electrons going plus 3 nickel, 2 plus ions going to 3 nickels. Now we have 6 electrons on both sides. So we know when we add these together, the electrons cancel out. Minus there. And we get our balanced redox reaction, which is 2 chromium plus 3 nickels going to 2 chromiums plus 3 nickels. Now in our nurse end, 6 electrons are being transferred. So our n's equal to 6. We do need to use the, pay attention to the coefficients here, because our Q, let me just write our Q, what Q is, because we're going to use Q. We need to have our value here. So Q is going to be product, all the aqueous products squared divided by the nickel concentration cubed. So sometimes you have more aqueous species than just 2, just one on the reactant side, one on the product side. When you have a more complicated reaction, you may have hydronium ion, you may have hydroxide ion. So you have to include those in the Q. In fact, that's what's in the problem I'm going to have you solve. That's what you're going to have. So we have to look up the standard. So the first thing you have to do if you're going to use the Nernst equation is to have the standard cell potential. So you need the standard half reaction potential. So I looked these up. So the standard cell potential, half reaction potential, reduction potential for the nickel reaction is minus 0.257. That's going on at the cathode. And the anode is chromium half cell is minus 0.744. Again, the half cell reduction potentials agree with where they occur. The higher half cell reduction potentials at the cathode and the lower is at the anode. So that's how we have it set up. That's correct. That matches our cell notation at the very top. So our E cell is E cathode minus E anode. So we have negative 0.257 minus a negative 0.744. We get a positive standard cell potential of 0.487. So here's our Nernst equation shown here. So it's E cell equals E standard cell minus RT NF over log Q. And since it's at 25 degrees, we can use this equation. E cell over E naught cell minus 0.0257 volts over N log Q. And so we plug those values in. We'll have the 0.487 volts minus 0.0257 volts divided by 6. Our N is equal to 6, remember, times log of 0.001 squared divided by 1.5 cubed. So I forgot to do that. So this isn't the answer. 0.58 volts isn't the answer. I didn't think that was very, it wasn't a very big number. Went up a little bit, which makes sense. But if you look at our original conditions, the nickel reactant, the nickel on the reactant side was 1.5 molar, is really high. So let me do this again, 0.001 squared divided by 1.5 to the 1.5 cubed equals a really small number. I hope this is correct. And then I'm going to take the natural log of that. and then I'm going to multiply it times a negative, let's see, 0.0257 divided by 6. That equals 0.06, then I have to add 0.487. I get 0.55, it's a little higher. I thought it'd be 0.551 volts is our E cell. So it makes sense that we have a lot of products, so the E cell is greater than the standard cell potential. Remember the standard cell potentials? All solutions, all species are 1 molar. And in this case, our nickel on the reactant side is 1.5 molar, and our chromium 3 plus on the product side was only 0.001 molar. So that's the answer there, 0.551. And I'd recommend you do this calculation too and make sure I did it correctly, that my calculator did what I wanted it to do. Sometimes that doesn't happen. So take care. That's the end of chapter 17. I think worksheet, I don't think, maybe 31. Maybe this one has to be, before we go on, there's another problem. There's a problem I want you to do. So work this one through. This was the easy one. I did the easy one. I left the hard one for you to do. So here's the harder reaction. And what makes it harder is the only thing that makes it harder is the balancing part. But this is actually a reaction that we balanced previously on the worksheet for 17.1. So the unbalanced equation is given. Permanganate plus bromide going to manganese, 2 plus ion plus bromine. And so the bromine half reaction, that's pretty easy to do. The permanganate half reaction has some oxygen, so you're going to have to go through that tedious process of adding water, then adding hydrogen ion. So this is an acid. It doesn't say that, but it does give you the concentration of acid, so you know there's going to be acid. So this, you want to balance this in acid. So I'll put this, I'll write that down, balance in acid. And then when you get the balanced equation, you'll know what n is going to be. That's important for this to solve this problem. And then you'll be able to set up your Q, and these are the concentrations that you'll use in your Q. So you're going to have a Q with permanganate, bromide, manganese, Mn2 plus. So permanganate, manganese 2, and hydrogen ion. So the Q, so the product, I think the hydrogen ion, the manganate, permanganate, and the bromide are all going to be on the reactant side, and on the product side, on the product in the numerator of your reaction quotient of your Q is going to be only manganese 2, and then in the denominator you'll have hydrogen ion, bromide, and permanganate. So give that a shot. Calculate the E cell for that. Your standard cell potentials for these two half reactions over here on the right, so you don't have to look them up. The last question at the bottom, this said, what would happen if you decrease the pH? Let's see, would decreasing the pH increase or decrease the cell potential? So think about it. I gave you a hint there. I said, use Lavoisier's principle to decide what happens to the concentrations of the reactants and products and which way the reaction is going to shift. So if it shifts more towards reactants, that means you're going to increase potential because you have more reactants, right? So more reactants increases the potential. If shift means the reaction has more, I guess, more fuel for the electrons. That's going to provide more electrons. If it shifts towards products, then that's going to reduce the potential. So that's what you need to think about when you answer that one. All right, so it depends on where the hydrogen ion turns out to be. My guess is you're going to have hydrogen ion on the reactant side, but I haven't balanced this, so I'll let you figure that out. So that's all for now. So take care. I think look on the website to see what worksheet that I want you to turn in. So that's it, and that's it for chapter 17. So next is an exam. So exam 3 is going to be on chapter 16 and 17, and I'll get that set up and post some information about it pretty soon. So take care. See you later, and good luck to you all on the exam.